So yeah, my name's Jeremy. I work for a consultancy called JUXT, part of a larger company called Grid Dynamics. And myself and a few other people in JUXT have been working on this very niche problem called a bitemporal database for a number of years. And one of our goals with even thinking about this is just this general vibe that we need to simplify software. The way we build systems is too complicated, and we're always on the search for better abstractions. You know, how can we simplify the systems we build? And that's what really I'm here to talk to you about today. So our main motivation is around safety and correctness. So I'll go into exactly what bitemporal means in a minute, but really the takeaway is it's about how confident can you be about the way that your data is stored and persisted on disk, and is it backed up, all that kind of feeling of safety, can you recover from errors? And then this more vague notion of correctness. So this is a more lofty goal, but we'll dive into exactly what that means. And whenever you're building an application, you really want them to be safe and correct. But when you build an application, you have really this dividing line in terms of the complexity, if you want to figure out how to make better abstractions. And the first thing to think about is this, what we call essential complexity. And really the only thing that in your application that is essential complexity is your business logic, of course, right? So the logic of your application. And everything else we call incidental complexity. And of course, there's all kinds of incidental complexity in the programming languages we use, the clouds we use. But in the financial domain in particular, we have all these sort of auditing, risk reporting requirements, and many different sources of incidental complexity. And the ones I've highlighted here, I think, are actually in some way solved by the bitemporal model. So what does bitemporal mean? Well, it's just two timestamps, right? You record the time that something enters the system, the ingestion time, and then you have a time that you want to report on. Maybe that's the exchange server time, maybe that's the time a trade was agreed or scheduled to be agreed, or the time a dividends are going to get paid. And you can actually think of these as, one is providing safety or immutability, as we like to talk about in functional programming circles, or if you work with event streams, this idea of not changing the past, you're always just appending to a log. That's the ingestion timestamp, and then the reporting timestamp is what the business cares about in terms of being correct. Now, this way of perceiving things is fairly natural, second nature. It's actually been great having a booth and talking to just a huge number of people that just get this problem. It's a very common thing. Outside of finance, the world hasn't really caught up with this message, right? Not thinking in these terms of these two separate timestamps. But I think it's like a very foundational part of the way we reason about time in general. And so if you think about the perception of the world and how that works in organisms, you're continually receiving data from different sensory inputs, and your brain has to make sense of when those different inputs actually aligned in practice. So innately, kind of as organisms, we are keeping track of these different timestamps. A bit more concretely, people like to think about these sort of feedback loops, especially when it comes to making decisions. Things like eyeball systems are really like instantiations of this idea of a observe, orient, decide, act loop, right? You just keep going around in a circle. And what we actually see in the systems that people build in practice is that they sort of build the observe system over here and then the decide system over here. And what we actually need are technologies or abstractions that help us to build these feedback loops faster and faster. So when I was at the OSFF back in, was it June, in London, I went to a presentation by Premier Lab, who I don't know if are represented in this room, but the word bitemporal was mentioned on the screen. I thought, okay, well, I'm observing the space around me. JUXT have only recently joined Phoenix, so I thought, well, I've been working on a bitemporal database for 5 years. Maybe you'd like to hear about it. So been observing this elsewhere. You see all these different vendors, and they all have bitemporal data models and diagrams talking about all this need for reporting over time. But it's not really like a solved problem. Everyone's talking about it. But actually, if you look at the tools available, you have things for doing as-of joins. You can do analysis of a time series data using KDB or QuestDB. If you want to do some data frame stuff, the Man Group have a good technology there. If you want to try and do this in Postgres, DRW sponsors some work on adding bitemporal tables into Postgres. And of course, all event streaming systems, anything that touches Kafka usually has this distinction between processing time and event time, right? So there's lots of sort of instantiations of this idea of bitemporality, again, which we'll come on to more specifically. But the question which has been a bit of an obsession for us as a team, and James is over there, we've really gone deep on this problem. We've been nerd-sniped into understanding the SQL 2011 model, which, as we all know, is like one of the beacons of what makes SQL great. But of course, no one's really heard of it. No one's using it. It was built designed 13 years ago. Oracle, DB2, SQL Server, they implement bits of the specification. But what we've really observed is actually there's been a lack of adoption in the database community of caring about these two-time dimensions that we know are really important. So there's been some really good sort of research and surveying of the field. This guy's got a great blog, and he talks about all the problems. Even though there was a standard created, the standard itself has a few issues. It's not complete. And he goes through the different databases and says, this one sort of implements it, but the syntax is a bit janky. This one sort of doesn't actually work in a way. And the performance of these systems as well is debatable, because a lot of these systems were built 30 years ago and before the assumptions about cloud object storage, this kind of thing. So as I mentioned, we've been obsessed about this problem. We've been building a database called XTDB. It's open source. We've got fairly modest community of users. We have people outside of finance even using this in say, healthcare and retail. It's built with, or version 2 is built with Apache Arrow, so we've really gone hard on this columnar data storage format. We think it's like a really important technology for the future of data interoperability in general. So whether or not it's a database from vendor A or a database from vendor B, in a few years, I think you're going to see Apache Arrow discussed a lot more. So we've been building this for a while, and it's been a bit of a passion project for JUXT. But what we've really wanted to do is to articulate the problem that SQL 2011 was always designed to solve and bring that into a more mainstream light, right? So a lot of people will be able to pick up Postgres, pick up MongoDB in their internal developer platforms. But in those systems, you have to solve the data compliance problem over and over again in very ad hoc ways. So you have audit tables, and you have triggers, and you have all these columns to keep track of versions. And all of this is ad hoc waste, essentially. Every project in the financial domain is having to do this versioning manually each time. So XTDB is trying to solve this problem. And I've mentioned SQL 2011, and that adds some syntax. So we have these ideas of system time and valid time. This is the name of the time dimensions that they follow, or the literature follows. And the important thing is that the syntax allows you to do things like, when you do an update, it doesn't destroy the previous record. Or if you do a delete, you can go back in time and see the old version of that record. Because the normal way of thinking about SQL is archaic, essentially. It was designed for the limitations 50 years ago. It's 50 years old this year. But SQL keeps evolving, and we want to push SQL forward and evolve the standard and add more grammar to respect this bitemporal model. So then it begs the question, well, it's been 50 years. Why has this been such a hard problem to solve? Because isn't it just adding 2 timestamps? And intuitively, it does just sound like add 2 timestamps to a table and you're done. Like, what's the big deal? But the more you look into it, and the more you look at the research and the thinking that's gone into this, people have been thinking about this since the 60s, basically. As soon as SQL was invented, the relational model was invented, people were wondering, well, how do you account for changing data? How do you go back and see the previous versions of your schema? And all the research in this led up to SQL 2011 as a standard. So SQL 2011, that's 13 years ago now. But that in turn was 40 years of research. And the reason you need this sort of more grounded way of thinking about it is because, well, how many dimensions is the right number of dimensions? Is 2 enough? Should you have 10? What's a chronon? Like, people have thought deeply about this topic and arrived at this model. So I didn't invent it, but we just implemented it. So concretely, what you're looking at is 4 timestamp columns. And the job of the database, of the bitemporal database, is to maintain the invariance. So this is actually just 11 rows or whatever it is of a single row in the database, like many versions against just the same ID. And the database's job is to make sure every time you do any update, any delete, it's closing over the previous system 2. So where it says system 2 null, that's essentially the current version where it says valid to null, that's the current version. Yeah? So when you're manipulating data in the database is working hard to make sure these constraints are met and that there are no overlaps and that every single ID has a version or doesn't have a version at a given point in time. And again, if you were to implement this yourself, there's a lot of triggers, a lot of SQL logic you have to implement to enforce this. So we've taken this principled model and built a ground-up database for this. So we actually implement this idea of the epochal time model. It's quite a grand thing, and if there's any Rich Hickey fans in the room, you may know what I'm talking about. But it's essentially this idea that you put the log front and center. I mean, this is what the sort of Kafka Confluent message has been for a very long time as well, is you put the log at the heart of the system and you derive views from it. And that allows you to decouple the writers from the readers. But this isn't how SQL was designed. SQL was designed for interactive transactions. You can open up a session, a connection, and do some stateful modifications and do some reads, and someone else is competing for locks on the same rows. But what we're saying is actually, yeah, maybe SQL needs to be compromised in some way to make it more auditable, to make it easier to work as a sort of a substrate for compliance. So yeah, we've tweaked the language and used the SQL 2011 dialect, the grammar, to implement this epochal time model. And what this means is that you can have a fully reproducible state of the database using just a timestamp. You can go back to last week, you can go back to last month, you can go back to last year and have consistent queries. You just have a query and a timestamp and you can reproduce results. Now, this, of course, has many applications. It's very useful for debugging. If you've ever written any code and gotten it wrong, it's quite painful to then figure out why it was wrong or what changed, and you want to say what was the difference between this state of the database and this state of the database. That's very useful. Also, if you want to scale out the number of readers in Postgres language, you have these ideas of read replicas. This is like read replicas for free. And to make this easy to use, unlike the SQL 2011 standard, where this is like you have to declare this table is bitemporal, this table has system time, this table has valid time. In XTDB, we've made it ubiquitous, and we've made it easy so that every change is, when you're programming as an application programmer, you don't have to think about it being versioned. You just, you make some updates, and the version that is the current version is the only one that's visible as of now. And that makes writing the application much easier, but you can be sure that then the history is still there should you need to go back and generate reports. And so this way of flipping it should make it a lot more attractive to developers, whereas before it's always something that had to be designed or baked into the schema. So if you want to access the old rows, of course, then you can have this extra syntax, for all valid time, for all system time, and suddenly these built-in columns can pop into existence, and you can access the history. So these aren't like hugely novel ideas. It's just no one has implemented this. No one has actually made this accessible in a way that your developers can pick up a database and start writing something which is going to properly maintain history. So we've talked a little bit about system time and why that's useful for debugging and read scaling. But valid time, why do we need two timelines? Of course, you want this sort of upstream notion of when something happened on the server. But the real reason is because there are all kinds of versioning requirements you'll hit in building an application. The most obvious one would be I need to make a change to the data because someone made a typo and a bug. And I don't want to have my as-of queries be affected by that bug. I want to hide the fact there was a bug. I mean, it needs to be in an auditable way, but essentially you want to be able to correct the data. Maybe you want to insert some data into the future. Like maybe you want to load some data, some payment schedules, and you can do that. It's a mutable timeline. You can change when it starts, when it ends. And maybe the best way of thinking about it is it gives the debuggability of system time, but for business users. Business users can then understand why did my data change, and it exposes the timeline to them. So every single version of any entity in the system from the user's perspective has this temporal mechanic. You can say this trade was valid as of this time with these properties, and now I want to talk about this other completely unrelated business object and then compare those two timelines. When did they intersect? When did they overlap? And so we added this language to make it possible. We also see a proliferation of technologies around change data capture, which is basically just this. It's taking versions of all the rows in the database. The question is then what do you do with that? Dump it into a data warehouse, which maybe you can do something useful. Wouldn't it be nicer if you could do the change data capture and analytics in the same system? That's kind of the vision there. So then we have some extra operators. So this SQL 2011 specification added these Allen interval operators. So you can say, did this thing and this thing overlap or precede each other, succeed each other? So there's a lot of flexibility there. This allows you to write very expressive, complex temporal analytical queries without having to do lots of less than, greater than, and reason about it. It's a very succinct way of talking about time, which again, is part of the SQL standard, but not many people are aware of it, not many databases implement it, and no one's, as far as we can tell, sort of solving the pain for the finance industry with SQL in a way that we think is possible. That's why we built it. So in terms of then very concrete use cases, like maybe the one that's the most interesting, and I was talking to Eric over there the other week about reconciliation and his experiences having worked in the industry for many years. And so reconciliation is just this idea that you have many systems, they all have inputs and outputs, and at the end of the day, you need to be sure that the systems line up, that they match, and understand the discrepancies, and be able to trace down things that have gone wrong. And maybe they've gone wrong for technical reasons, or maybe they've gone wrong because someone's doing something a bit dodgy. And so the job of reconciliation is taking these different timelines and trying to make sense of it. So in maybe more typical example, in any kind of trading system, you'll have these different timelines, these different evolving states, where you may have some very complex objects. A lot of people use MongoDB because they just want to throw some JSON in and worry about versioning later, in a sense. But in this system, you can do all of this in SQL and reason about when these things happen at the different points in time and check that things happen when they were supposed to happen. So that's like a use case which I think a lot of people can relate to. The one which actually inspired XTDB originally was in the risk domain. So risk, as far as I'm aware, and I've not worked in these systems directly, but it requires a lot of simulations, a lot of calculations, and the requirement is to be able to reproducibly report on your positions, the state of the portfolio. And so in a risk system, you want to be able to version the inputs, you want to version the calculations, and you want to know when things change and trigger new calculations. And so I won't labor on this example too much, but in our documentation, we've gone through various things that risk people would like to do and the way they want to think about storing versions of data and avoiding having to copy large amounts of data over and over again. And you can do that with just a timestamp. And then machine learning is another area where time is a really important concept. So again, it's not something I've spent my career so far thinking about too deeply, although machine learning in databases is a very interesting topic. But if you're doing generative AI or you're doing anything involving something that needs backtesting, obviously quants do a lot of backtesting, you need to make sure that the data you're backtesting on is accurate and be able to understand that when that data changes, it's going to impact the quality of the results returned by the algorithm. And so this isn't like a novel thing. People have been building out these feature stores for years. Hopsworks is quite a prominent vendor in the feature store space. And they have some really good blog posts about the importance of having the two timestamps, right? One for the correctness of the data, and then the other for ensuring that you can reproduce the inputs and the outputs. And they actually use DuckDB, which has an as-of join. You've already seen QuestDB had an as-of join. KDB has an as-of join. This is essentially the same as the SQL 2011 model. And actually, that Hopsworks paper, they write about the comparison with SQL 2011. And so maybe if we all built our applications using SQL 2011, or something inspired by it, that would have the ability to add machine learning into our applications and complete the OODA loop, right? We can observe, we can orient, we can decide, and we can act within one system, right? Rather than having a data warehouse operational team building an OLTP system and doing transactional workloads. Time travel could be actually a really important thing, not just for machine learning, but even for just making decisions as business users. So Kent Beck is famous for XP programming. He talks about eventual business consistency as the best way of explaining the importance of bitemporality, especially for non-finance people. It's just making sure that things are easy to reason about. And so as we evolve and push systems forward with AI, maybe time is going to become the more important factor than all. So there is an elephant in the room we haven't talked about, which of course is Postgres. And it's becoming the popular default. Like we've finished the NoSQL era to some extent. I know MongoDB is still succeeding, and that API is being rolled out more and more. But is it for the right reasons? And in 10 years, are you going to regret not having SQL? Because all the database researchers think that SQL is here to stay, the relational model is here to stay, and as more systems come online, they're going to implement SQL and make using non-relational data from SQL easier. But crucially, Postgres, it's been out for 13 years. Postgres has not implemented this bitemporal standard. Why not? Well, because it's really hard, because Postgres was written a long time ago by a very smart man who's a legend in the field. But the way it assumes how data should be stored in rows, not columns, the fact that hard disks were limited, just means that Postgres is unable really to properly implement bitemporality, at least if you want to take advantage of cost-effective object storage. So yeah, what motivates me and our team is this opportunity really, because Postgres isn't going to be able to keep up. And actually, if you speak to experts, as I did earlier in the year, Victor Leis, very, very highly cited database professor, he does research that shows how Postgres is 2 or 3 orders of magnitude slower than actual hardware limits. It's a very slow database by modern standards. SSDs are tremendously fast. And he actually thinks in terms of the internals of the code in Postgres, it's not possible to save it, he says. It's not possible to save. And I think we'll see that pan out, whereas as Aurora and Google's managed SQL services, as Azure's managed SQL services, they will offer Postgres compatibility, but what's going on under the hood? It's not going to be open source Postgres, because ultimately it was built for the wrong era. So what we've done in XTDB is to keep the Postgres vision alive, but through the same way as everyone else is doing, which is implementing or emulating the Postgres wire protocol. And this is a way of bridging the divide that every new database faces of how do you make it accessible? How do you avoid the risk of having to train and build lots of new collateral to help developers understand how to use your database? Well, if it looks like Postgres and it feels like Postgres, then maybe it's good enough. So here you can see, we implement the Postgres protocol so that PSQL or other Postgres tools can talk to XTDB. Now, of course, we're not the only people to have ever implemented the bitemporal model, but I think we're the people that have done it the most intuitively. And so I have a quick demo just to show you what I mean. So if I unify outputs and go to, well, first of all, actually, has anyone seen TraderX? Any heard about TraderX? Well, anyway, Finos have been working on this for a little while. Morgan Stanley donated it. And we spent a bit of time over the summer just integrating XTDB into TraderX. So normally it's like an H2-backed database system. So each microservice has an H2 in the back end. But we wanted to add reporting. So we took the TraderX UI, we added some pricing data, and we added a reporting tab. And on that reporting tab, you can then slide across the version history and see the full history of your trade data in the blotters update to reflect the history of that data. And you can then use the as-of pricing. So we did this because we wanted to try and articulate the actual end value to the end user of time travel. It's a really powerful capability in the hands of the right people. I don't know all the kinds of things that traders in practice would want to scrub across, but we've spoken to enough of them that we know it's an important capability. So anyway, that's like a UI to look at. Here I have VS Code. It thinks it's talking to Postgres. You can see the little elephant up there, but no, it's XTDB. We can see here we've got nothing in the database. We've got nothing in our trades table. Our trades table doesn't even exist. But we can insert into it without having to do a create table. It's more like a document database in that sense. It's more like a MongoDB. You can insert arbitrary nested data. And then we can run our select star from trades again. And here it is, that data we've just inserted. I'll just close this. So that's just some nested data. It's fully typed. It's not JSON-B, so you don't have to lose lots of, it's crazy that JSON doesn't have a timestamp representation, and how can we make a temporal database without the ability to discuss times? So we have that. You can select star from trades and see that. If we want to do an update, and this is when it gets interesting. This is when, if you didn't have this innate capability, you'd then have to write some triggers. Your SQL would be several statements long. You'd have to do it in a large transaction and hope that it works and is efficient. So here we can set the price. So right now there's no price column. And if I set the price to 110, we should see that when we run select star from trades again, we get 110. And if I set it to 105, we'll see now says 105, right? So it's showing us the latest version. It's not showing us all versions, which is what the standard says. The standard says if you do select star, you show all versions. Anyway, it's a bit of a rant. We can go into the nested data. We can access the nested fields. Again, very sort of MongoDB-like. So here we're pulling out the foo from our, what was it, the allocations array. But if we want to see all versions, we can do that. We can do select star for all valid times. So every table has the ability to remove this filter, and we can see the 3 different versions we've just inserted. We can also very easily work with nested data and return nested data. A lot of people spend a lot of time with GraphQL building these very complex resolvers to avoid the n+1 problem, whereas we have some syntax to allow you to easily retrieve nested results. Again, it's actually like small things you can make changes to SQL to make it a lot more ergonomic for what people want in the modern world. And so DuckDB is another example of this. Like DuckDB have a whole friendlier SQL mantra where they're not waiting for the next SQL standard to be agreed by committees with ISO. They're going ahead, plowing on building features that developers want and analysts want. So in this example, we can pull back the trade, but we can also pull back the history of the trades as another column in the database, right? In the result set. So without having to issue multiple queries, we can just pull back some data, and it's easy. We have the ability to exclude things and pull back one result. So again, some more syntax there. And I mentioned this epochal time model. All transactions have an ID, unlike Postgres, where it wraps around and you have to remember to handle that, the once a month or whatever when it happens. Here, the IDs are permanent. You can reference them. They're stable. You can attach information to them. You can pass them around to other users. So, analytics application A can pass a timestamp to analytics application B, and they can be talking about the same thing, and that's very useful. We see this a lot in big data with Iceberg and Delta Lake. These systems, they do support this as of, because it's important. Not many OLTP or transactional systems can do this, and you would spend a lot of energy trying to recreate this functionality on Postgres. Here we have the ability to rerun the query as of a time. So right now there's nothing in the database because I need to update the timestamp. If I put it into the future, say, we should see, maybe it needs to be a bit further. There you go. So now we've got some data. This is the latest data we inserted. So very easy. Again, we've added some syntax to make that easy. Because if you didn't have the syntax, it would be like where, and, less than, greater than. It's going to be full of bugs. We can see the schema has evolved. It reflects the unions of all the columns. So it is a fully typed system. We're not just storing blobs. We are understanding the types. We're storing it in a columnar format, which means it can be compressed. And we're not having to have all this concern about, do I need to have 10 times the amount of space to store the history of the data? Well, it really will only store or significantly store the data that actually really changes. So it's a problem you should push down into the database layer. So if we want to insert things, we can insert into the past. So we can specify the value from on the insert here. So we're specifying 2020. We want to make sure that if we were then to run a report as of 2021, we'll see that trade because we've put it into the past. So if I select star right now, you'll see 2 there. But if I do for valid time as of date 2021, there you go. It's there. The database only was created 10 minutes ago, but we're inserting stuff into the past and can reason about what happened 4 years ago. We can also put stuff into the future. So in this example, I'm going to press this run statement, and if I press select star right now, we're not going to see the price is still 30. If I run it again, it's still 30. If we wait another couple of seconds, it's 50, right? So we're putting things into the future. How many people have been waiting patiently for a batch process to update at a given time and then see it's failed? It's like, wouldn't it be nice if you could put things into the database's future time? What else do we have? We have the ability to, let's look at, for a given trade, let's see all the intervals where it was valid. Let's see all the version data. Of course, we can do that. And then we can use that information to say, show me all trades that overlapped with this trade. By given an ID, we can use this overlap syntax. So we discussed that earlier. And we can see the the two trays, ID1 and ID2, they overlapped, and they overlapped at these times. And we can delete. Of course, it's important to delete from systems. You don't want to clutter up the system with lots of stale data, and you can do that. And if you ever need to get it back, you can, of course, do that. But the application, by default, won't show you that data, right? The data is hidden. It's a soft delete. We do have the ability to erase data if you need to comply with rules and regulations or data retention policies. And you can audit everything, which is the main point, really. It's like, as a regulated industry, you can turn your database over to an auditor. They can write some SQL, and they can quickly understand what did a person in your organization know at a given point in time. And that's quite an important capability, I think, for the future. So that's the end of the demo. I will just go back to the slides, and let's go back to this one. So I mentioned TraderX, right? We have a booth. If you want to see a demo, I can do the live thing. I didn't want to run it at the same time as the presentation because it's about 30 Docker containers, and my laptop's probably going to die if I try and run it all at the same time. But please do say hello and chat. Yeah, importantly, we're just a small group of engineers on the side of a consultancy, now bought by a bigger consultancy. But we're here talking to you because we're just interested to make connections and to find people that have temporal problems that could benefit from this kind of technology. Because we don't see AWS or Azure or Google they're not going to solve this overnight. No one's tackling this. It's going to have to come from us, I think, if we want to see a solution to this space. We've been building XTDB because we want to try and solve this for organizations like yours, and we'd like to collaborate through Finos to make that happen. So yeah, please get in touch. We're really happy to talk and to see if we can make this a reality for you. So yeah, thank you very much. All right, any questions? Yeah, so right now, in the interest of simplicity, we wanted to build the database in layers. The easiest way to manage data over time is to not care about the schema. So in a sense, it's more like a schemaless database right now. But the idea is that every time you do an alter table or constrain the schema, that could be versioned. We haven't implemented that yet, but if that was important, we can do that. But yeah, essentially, you have 3 axes at a time, really, because the schema is evolving as well. And XTDB in its current state can help track that. But yeah,
Will it work? Right now it doesn't support it. Like if I do alter table at some point in time in the past.
So right now we don't have an alter table. Alter table will fail the grammar because we haven't implemented it. You don't need it. Maybe you do need it if you want to have the constraint. But yeah. OK. Any other questions? Please. So inspired by Datomic. So we haven't used Datomic's code. We're not affiliated with them, really. So Datomic is another temporal database. It's seen some success in the financial space because of this good versioning ability. But yeah, we've written a bit of it in Clojure, like we are Datomic fans, essentially. And we want to bring that power or that vision that Rich Hickey had to the world through SQL databases. Yes, so right now we're at the sort of hundreds of gigabytes level. We're not really testing beyond that because that's already enough to locate the bottlenecks we do have. But we're built on S3 storage. I guess our motto is correctness is the most important thing. Performance comes second because a lot of databases make the wrong trade-off. We would like to scale it up, terabytes, petabytes. There's no reason why it shouldn't be able to. It's just a question of engineering time and resources. Right now, it's not focused on huge scale. But it should at least be very low cost compared to having lots of Postgres clusters all running statefully. In this, we've separated storage and compute, so you can spin up compute and query the object storage and then shut down the compute again. Well, in a sense, it's last writer wins, but every writer has the ability to see all the other writes previously. We linearize the transaction log, which means the isolation level just prevents any sort of race conditions or conflicts from happening, which is quite an important part of what we think makes resilient information systems is being able to know you're at state A and then state B and then state C. A lot of, Postgres has a snapshot serialization isolation level, And that was implemented, I think, in 2012. And it went for like 8 years. There was a Jepsen report written about Postgres, or the guys that do Jepsen, they analyzed Postgres, and they found a bug in the multi-version concurrency control in Postgres that had been lurking there for 9 years. Just sort of, no one had looked, no one had exercised it enough, because it's so hard to build correct concurrent systems. So XTDB is a more sort of simple, dumb design. You have one write-ahead log, or one log of transactions that's serially ordered. And actually, modern hardware makes that actually quite fast. Like CPU cores are much faster than they were 20, 30 years ago, and a lot of write workloads can be supported.
Is there a space trade-off with storing data by columns rather than rows? You have to maybe store a row ID for column.
Actually, columnar data generally is just better all around for the space trade-off. The thing actually trade-offs columnar data. If you need to query the whole row, you have to fetch a bunch of column files. So actually, in terms of space saving, columnar data always wins out. The read cost can be slightly higher if you only want to fetch a small amount of data.
And bonus question, what are you using to implement this? Something like C, Rust?
So we're on the JVM. JUXT consultancy, we had a background in Clojure, then we've been doing Kotlin in more recent years, and there's some Java, but it's basically a JVM company so far. But yeah, I mean, we've got our eyes on Rust, and if we were already Rust developers, we probably would have written in Rust by now. But
Clojure, Scala?
yeah, there's no Scala in the code base right now. But yeah, you can, because it's Postgres, like you don't have to think about the implementation language. That's our job.
No,
You focus on the SQL. Cool.
Thank you very much for existing tables. So it's like the best future, maybe.
Yeah, so right now, the schema just grows. Every time you add a column, it's there forever. You can't remove the column from the table. But you can introduce new columns anytime from one transaction to the next. There's no separate or explicit schema changing operations. So it's more like MongoDB in that sense. Hi.
If I think of like streaming technology, like Kafka or whatever it is, a transaction, I can tag things temporarily and store them. Is the advantage of doing it through XTDB the speed of your SQL queries when I'm trying to access this in real time?
I think the advantage is pushing the complexity of figuring out the best query plan to the database, right? Application developers shouldn't be essentially writing their own query compilers or like query execution engines more than strictly necessary, right? SQL is fundamentally a good idea. I think when people push back against SQL, it's because the query optimizer did something bad, right? And there are always limits to what query optimization can do, but I think at least in the first instance, everyone should be writing SQL. Well, maybe not SQL, but like something declarative, something relational, because that is the most succinct way of expressing a problem and getting a solution. Once you want to make it fast, then you worry about exactly how this compiles. What does the machine code look like? Where is the storage? How do I optimize locality and compute? And yeah, I think in the streaming space, a lot of very advanced thought has gone into this. So we haven't talked about tailing a query, for instance. A lot of people say, well, I just want to see. I want to run this query and then just get a stream of results. XTDB does not do that right now. But this model is a good foundation for building that. Pleasure. All right, I think we're done. Thank you very much.